All right, section 3.9 is about the derivatives of exponential and logarithmic functions. These are your very last derivative shortcuts from chapter 3. It's been a lot of derivative shortcuts so far this chapter. We're going to do some proofs, and we're also going to just have some derivatives that you have to have memorized. So the first one is the derivative of e to the x, which we have talked about a little bit, but if you look at this graph of e to the x, if you look at just a given point on the graph, and here's a tangent line for that point, notice how the slope of the tangent line is up 1 over 1, and the y-coordinate at that point is also 1. At this point, I don't exactly know what the slope is, but it looks like the y-coordinate is about a half, and it looks like the slope is also about a half. So this is one of the derivatives that you just have to memorize. The y-coordinate matches the slope, so the derivative of e to the x is itself. It's e to the x. We're not going to prove this because it involves a limit that we'd have to just accept as truth anyway, so let's just accept the derivative as truth. One thing to be aware of if you are doing a derivative of e to the x is that if it involves e to anything other than just a plain old x, it's going to have a chain that goes with it. So this is e to the sine of x squared, so it's actually a chain of chains. So if I'm going to take this derivative, I would start with the derivative of e, or e to the, and that derivative would be e to the sine of x squared times the derivative of sine, which is cosine, times the derivative of x squared, which is 2x. There's not really a lot of simplifying I could do with that, but I could rearrange the way it's written, and it would still be equivalent. I'd like you to take a minute and see if you can remember the log properties for that you learned in pre-calculus. I want you to be aware that the log properties hold no matter what base log you have, but if you have log of a times b, you can rewrite that as the sum of log of a plus log of b. And this is, I just want to really point out, that's also true of natural log. It's true of any base. So that's the multiplication property. We also have a division property, so if you have the natural log of a over b, then that's the natural log of a minus the natural log of b. And then really the most useful thing about logs is this exponent property. So if I have natural log of a to the b, then I can pull the b down in front and just have b times natural log of a. That's really powerful for solving exponential equations. That's basically the whole reason we have logs. And then the change of base formula is also handy in some of these proofs. So the change of base formula is if you have log base anything, let's say 2, of a, you can turn that into a natural log really easily by making it natural log of a divided by natural log of 2. You might notice that we have really strong preference for natural logs in calculus, and part of the reason for that is after today's lesson you'll see that the derivatives for natural log are just prettier than the derivatives for any other base. So we're going to prove this derivative, the derivative of a to the x. We're going to make use of e to the x to prove it, and you're responsible for knowing the derivative. You don't have to prove it every single time, but since this is a calculus class, it's a college level class, I want you to be exposed to proofs. So if I look at y equals a to the x, the first thing I notice is that I have an x in the exponent. So I'm going to natural log both sides to bring the x down. So I have natural log of y equals x times natural log of a. And then I would like to get rid of this natural log, so I'm going to exponentiate both sides, or e to the both sides. So this would become just y, because e to the natural log undoes itself, and so then I have e to the x times natural log of a. I'm going to put a little note here. Because e to the and natural log are inverses, e to the natural log of y is just going to be y. That's where this comes from. Okay, notice that I have only ever followed the laws of algebra by doing things to both sides, so these two expressions are equivalent. Okay, I'm going to take the derivative of this one, of the one that we just wrote, because I have a rule for taking the derivative of e to the x. So if I take the derivative, I get dy dx equals e to the x times natural log of a times the derivative of x times natural log of a. And I'm going to put another note over here. Natural log of a is a constant. I don't know what a is, but this is really about trying to figure out the derivative of a number like 2 to the x. So natural log of a is a constant. So when I take the derivative of a constant times x, the derivative is just the constant. Now this would be a perfectly good answer, but it's not the most beautiful that we can do. The most beautiful we can do is notice that these e to the x natural log of a is right here, but that's equal to y, and y is equal to a to the x. So I could write this a little bit nicer if I write it as a to the x times natural log of a. So if my function is a to the x, my derivative is a to the x times natural log of a. Okay, we're going to use that derivative. So if I want to do this, I'm going to take the derivative of this equation because I want to know where the slope is equal to 2. So that's where the f prime is equal to 2. So this derivative is 3 to the x times natural log of 3. And we want to know where that's equal to 2. This would be a calculator active question, so you'd have a calculator in front of you for solving for x, but you'd still need to know the steps. So we could divide both sides by natural log of 3. And then we could natural log both sides. And then we can solve for x. And then, because you're in AP Calculus, all of your answers should be correct to 3 places to the right of the decimal. What calculus means by that is that you can either truncate or round, but you need to be able to report 3 digits to the right of the decimal correctly for that. So when I type this onto my calculator, I get x equals 0.54532, etc. But I really only need to be correct to 3 places to the right of the decimal. Please make sure you're not rounding at this step, because your final answer has to be correct to 3 places to the right of the decimal. All right. We're also going to prove the derivative of natural log of x, and then we're going to summarize all of the derivatives that you should know for this section. So the way we're going to prove the derivative of natural log of x is we're going to think of this. Remember, natural log means base e. So if I write this in exponential form, I get e to the y equals x. If I have that, then, so this is just exponential form. Then I'm going to take the derivative of both sides. So I get e to the y times the derivative of y equals 1. Then I'm going to solve for dy dx. And then we're going to notice that e to the y is the same thing as x. So when we rewrite this, we can rewrite it as the derivative is just 1 over x. We like this answer better, the 1 over x answer better, because our function was given to us in terms of x. We'd like our derivative to just be in terms of x as well. All right, I'm going to skip ahead for a second so you can have the rest of the derivatives that you need to know. So we talked already about the derivative of e to the x is e to the x. The derivative of any other number to the x is going to be that number to the x times natural log of that number. We did the derivative of natural log of x is 1 over x, and I'm just going to ask you to believe that the derivative of log base a of x is 1 over x divided by natural log of a. This one actually follows really closely from change of base formula. If you take the derivative of log base a of x after you change the base, it follows really closely. So you could change the base to natural log. So you could try that on your own if you're interested. All right, now we're going to do some problems. So this is a really good type of problem. This is a type of problem where I didn't tell you the x-coordinate. I didn't tell you the slope, but we're going to use slope, the big broad idea of slope, to figure out where this tangent line is. So I have a tangent line somewhere on the graph of natural log of x that passes through the origin, and we want to figure out what its slope is. So notice that I labeled this point on the graph as a comma natural log of a because I'm not sure what the x-coordinate is. Looks like it's somewhere between 2 and 3 in my picture, but that's just kind of a guess. Okay, so there are two ways of thinking about slope. There's an algebra way of thinking about slope, which is a y2 minus y1 over x2 minus x1 is going to be the slope. Okay, since I labeled my 2 points, I have the origin, which is 0, 0, and I have a times natural log of a for my other point. I can figure out algebraically the way the slope is going to be equal to natural log of a minus 0 over a minus 0, which means my slope is going to be natural log of a divided by a. Kind of stuck there. I still don't know what a is, but I have an expression for the slope, and that's all just thinking about slope algebraically. I can also think about slope in a calculus way. So the slope is going to be the derivative at a, according to calculus. So if I take the derivative of natural log, I get 1 over x, but at a it would be 1 over a. Now, I have two different expressions for the slope, and unless either algebra or calculus is full of lies, those two expressions must be equivalent. So I have 1 over a, the calculus way of thinking about slope, is equal to the natural log of a over a, the algebraic way of thinking about slope. These are two fractions that are equal to each other. They have the same denominator, so the numerator must be equal to each other. And remember that natural log is base e, so a would have to be e to the 1 power, which means the slope is going to be 1 over e, because the slope is 1 over a. All right, that's kind of a fun problem. It's one that you should be comfortable with. I'm going to stop there. I'm not going to prove the derivative of log base a of x, but that is the lesson for logs and exponentials.